So once again, good morning, everyone. And today we have the last session, last day, sorry, and the first session. So we are going to start with the Fabien, next our keynote session for today. So it is a great pleasure to introduce him with all of you. So Fabien's PhD in 2002 pioneered the joint use of distributed artificial intelligence and semantic web to manage a variety of data sources and users above a web architecture. Then, as a research project leader at Carnegie Mellon University, USA, he proposed an AI method to enforce privacy preferences in querying and reasoning about personal data. In 2004, recruited as a researcher at INRIA, he started to study models and algorithms to integrate social media and knowledge-based AI system on the web and support humans in the loop. In 2012, he became the representative of INRIA at W3C and founded Vimix on bridging social and formal semantics on the web with AI methods. And he became a research director. He successfully supervised several 15 PhDs, chaired major international conferences, and authored many journals, papers, conference paper, workshop paper, books, and book chapters. He also initiated a series of bilingual MOOCs on semantic web and linked data, and he was selected by an international jury for a chair of 3i Côte d'Azur on AI. From 2018 to 2022, Fabien was vice head of science of INRIA Sofia Antipolis, Mediterranean, and he became co-president of the scientific board of the Data Science Technical Institute in 2022. So please join me to welcome Fabien here. And thank you, Fabien, for accepting and for coming here. So please take your session.
Thank you very much. Thank you for the time. Okay. So before I go into topic, I'd like to say two things about the presentation. First, in this presentation, I tried to include as many extracts from testimonies of other groups than mine, especially from companies, because I would really like the points I'm making not to be my points, but backed up by other groups, other teams. And secondly, I want to acknowledge the fact that the work I'm going to present you from my team is really based on many people. So my team is based in the south of France. It's called Wimix. It's a joint team between INRIA, CNRS, and University Côte d'Azur. And if you look at the people in my team, you will find very different skills. People working in natural language processing, people working in knowledge representation and reasoning, AI in general, argumentation, HCI, human-computer interaction, but they all have one keyword in common, knowledge graph. They contribute to one of the steps, at least, of the life cycle of the knowledge graph. And that's what makes the Wimix team. Okay, so we are going to talk about knowledge graph. Now, this is the knowledge graph conference. I could skip that slide, but what I would like to insist on is what I would, in that talk, what I would consider as a minimum requirement to be talking about a knowledge graph. Okay, you can add plenty of other things compared to what I'm going to say, but at minimum, from a mathematical point of view, it's going to be a directed label multigraph. And in that graph, the idea that, first of all, instead of talking about tokens or strings like Paris, we are going to name things. We're going to have named entities. We are not going to consider only these entities separately, but we will be interested in the link they have together. So we are going to talk about linked named entities. And more precisely, we will be also interested in the types of links they have together. So named relations. Named relation between named entity in a directed label multigraph is going to be the minimum things I will require to be talking about a knowledge graph. And then you can add schemas, inferential schema, validation schema, many important things, but that's the minimum I will be building. So typically they support associative data, so data sets where we have a strong associative dimension, and they are very object-oriented friendly structure. They are known to be easily extensible, and you can change them. That's really very easily. You can change the data, you can change the schema. We sometimes say they are loosely coupled to the schema. You can run complex queries on relations on them, and you can run validation and inferential schemata on them. As I said, I will, on a regular basis, I will try to get some testimonies from other actors in the domain. So if you check the webpage of Oracle, for instance, they say that graph databases are increasingly being used as part of data science as a way to make connection in relationship clearer. So again, they insist on this associative dimension of the data. And they also give example of a query which is much easier to write on the graph structure than on the relational one. So you all know that these have been adopted, these knowledge graphs, they have been adopted in many domains. So encyclopedic knowledge, geographical knowledge, gene knowledge. Peter talked about genes yesterday. Financial knowledge in fiber. Many domains have knowledge graphs. And we even have we could say a hall of fame of some of the knowledge graph with Wikidata, DBpedia, Yahoo, Freebase, and so on. All right. Now, sometimes when we go to conferences like this one, or ISWC or ESWC, there are participants asking, how can we convince people out there who are not using knowledge graph that yes, knowledge graph are great, looking for how can I say arguments to make for that, to convince people who are not using it. And so my first reaction is, when you look at big players like Microsoft Bing or Google, who have a knowledge graph, they have a knowledge graph with billions of real entities in them that feeds the knowledge graph panels in their search result, and they have APIs for that. The first answer we can have is, in fact, everyone on the web is using knowledge graph, because as soon as you run a search on Google or on Bing, this part of the result comes from a knowledge graph. So at the risk of being a bit dishonest, the question is rather who is not using a knowledge graph? Because every time you run the search, you are tapping in data. If we look at one of the latest reports from Gartner in the industrial domain, they have positioned the knowledge graph at the very core of their radar, and they have chosen to identify it not just as a important technology in itself. They have typed it, they have classified it as a critical enabler. So not only is it a technology which is important in some of our solutions, it's also a technology that is enabling other technology. And we see that a number of companies out there now are using knowledge graph as the basis to build their AI stack. In the academic domain, clearly also, there is a growing interest in knowledge graph. This is the total number of publications having knowledge graph in their title in the past years. And if you look at conferences like this one, or ISWC or ESWC, there are many hot research questions going on, from how do we formalize the knowledge, store them, validate them, verify the quality, enrich, extract, secure the access to a knowledge graph is a hot topic now. Traceability, provenance, decentralization with approaches like Solid, for instance, analytics, mining and learning on the graph, and of course, interaction design and visualization. So a very, very active domain, right? In that domain, I am going to position my team and my work in a subdomain, something in which I really believe in, which is the one of using open standards for knowledge graph, and not just any open standards, the one of the W3C. I really believe in using these open standards, and they have been working since 1999 in building a growing and impressive stack of standards at W3C to exchange knowledge graph using different syntaxes, to validate them, to query them, to enrich them, to bridge the knowledge graph, the RDF stack with other formats stack. And so when I will be talking about knowledge graph in that talk, I will be, in fact, saying that in my group, we're using RDF to represent this data. We're using RDFS for the lightweight ontology. And when we need more expressivity, we will be using one of these constructors from OWL to augment the expressivity of our schema. When I need to access this knowledge graph, I will be using the open standard Sparkle, which is a protocol and query language and result format to access RDF. And when I will be talking about validating or documenting shapes in a knowledge graph, I will be using the SHAC standard. In addition to that, everything I'm going to mention today, and all the approaches and application we do, is implemented using an open source library, which is called Corel. The first line were written in 1999 on the first draft of RDF, and they still maintain at INRIA. It's a library, it's a server, it's a command line system, and it also has a very simple GUI, which is heavily used for teaching purposes. And it implements all the standards as well as the extension that we propose in my group. These knowledge graphs are on the web, and therefore we also apply, and everything we publish in the team apply the linked data principles, which means our URI are dereferenceable. Every time we access a URI, if we're human, we negotiate a human-friendly version in HTML. If you are a program, a machine, and an AI algorithm, you get some data in your preferred language. And so following these principles, just like in the 90s, there was an explosion of the number of websites for human online. In the years 2000, we had a growing number of linked open datasets online. And in my team, for instance, we contribute to that cloud. One of the first contributions that we are maintaining and publishing since 2012, the French chapter of DBpedia, which is 300 million extracted triples and over 1.8 billion queries per year, an average of almost 4 million queries daily on that open calculating point. I will come back on the case of DBpedia because it's one of the research questions in my team right now, is to improve the extraction of the knowledge, because we want to go from a page like this one to a graph like this one. And the way it is done in DBpedia right now, we are missing a lot of information. For instance, we are not tapping into the text. And that's one of the questions we are looking at right now. We published data set on the COVID during the pandemics, enriching them. We published data sets in the music domain. So we have 2 million rock songs data sets, which is available in RDF with the tones, the NLP analysis of the lyrics, and also the sound analysis of the soundtrack, all of them represented in RDF and ready to be used by anyone who wants to run their algorithm on such data. In the robotic domain, we'll come back to that too. We published data, for instance, to provide common sense knowledge to a robot. Help a robot know that if it is looking for a fork, it might as well start by the kitchen before running its image recognition algorithm. Of course, there is also linked open vocabulary. We have many vocabulary that are published on the web, the link of data, and we contribute to that. There is even an namespace server at INRIA where we publish our vocabulary following the linked data principles. Vocabulary is in many domains. So MUNC is representing uncertainty. PKSO is the possible world Kripke's structure representation ontology. And NLV is the normative requirements vocabulary and so on. And this made us think of the fact that the community has been working on many great tools for editing ontology, for instance, the desktop version, the web version. But we are still in need of tools for ontology because there are many different practices. So one of the latest results from my team, one which we released a few weeks ago, actually, and that I wanted to mention, is called Olivo. So Olivo, it's a reference to Asimov because it's an implementation of the Asimov methodology for ontology engineering. This methodology is based on GitHub. So it's a GitHub approach to ontologies where we edit, share, and validate ontology on GitHub repository. And we even provide a GitHub template for that. And the workflow is also automated for continuous development and integration of the ontology of the schema. Every time you push a modification to the schema, it is first checked according to some classical rules, such as the syntax validation, which is over there, but also some project-dedicated rule. For instance, in that ontology here, the community of that ontology wants every class and every property to have a property is defined by, so a link back to the ontology where it is defined. And so if someone breaks the rules, there is a report which is pushed in URL using the URL ontology to represent reports result, and in Markdown for human and integration to the GitHub. So it's a complete GitHub environment to collectively develop and check ontologies. Do not hesitate to check it and find issues if you find issues. All right, thank you very much for the water. So now in the rest of the presentation, I'm going to select, let's say, 3 families of application domain or application scenarios and give some example in these ones. There are many, many more. That's the one I chose for the remaining 40 minutes in the talk. So one of the first testimony example is one of the oldest one, and because we are in France, I took a French one. The one I wanted to mention was presented at TSWT in 2012 from the Renault car manufacturer. They explain how they use RDF, and I found it very interesting because I found the approach and the object they are identifying very original. The problem Renault has is that they are manufacturing car, and if you consider all the possible configurations of all the models of cars, it's 10 to the power 25. So it's a huge space. Okay. One of the problems is when they have to talk with a subcontractor, with a garage maintaining, a provider for the parts and everyone, they have to make sure that a given configuration exists. Because only, with big quotes, only 10 to the power 20 are coherent. The other ones do not exist. And so they had this idea to give URIs to all of them. So they identify all the configuration. They came up with a scheme that allows them to generate a URI for any configuration. And then they provide a server where if you connect, if the URI answers the configuration exists, if you get a 404, the configuration does not exist. And in addition to that, they can pre-compute things such as passes, constraints that exist between the configuration that allow you to move from a configuration to another, or on the contrary, that tells you they are not compatible. And this data is directly published online, used for communication between the different actors, but also between the different applications to move from an application to another. More recently, Volvo published a testimony. So every time I give testimony, I put the source here if you want to check them, explaining how and why they use knowledge graph. And so they explain that they have many vehicles, again, many configurations, so a little bit like Renault. Customization offers demand, and many dependencies between all these aspects and the different actors. And so they came up with the Volvo car graph intelligence platform, which it's really oriented to manage the different data silo and connect them. So clearly, it's one example of one of the most well-known usage of knowledge graph, which is to connect the different data silos inside the company, and also to contribute to the urbanism of your information system. Okay? They use it to manage connected data, to transform complex data into a uniform graph, to analyze the data for decision-making, and in general, to make sure that a given data set is not locked in its silo in one of the subsidiaries of the company. A third example in that category I wanted to give you is not from one company, but from a consortium. this consortium, everyone in this room knows it. You may not know the consortium, but you know the main object they produce. They are the guys doing the barcode on every product, okay? The GS1. And they released a joint letter with W3C explaining why they believe knowledge graph are important for that. They believe that the knowledge graph are important for enabling circular economy. So what they defend is that knowledge graph is the perfect structure to follow a product from the moment you chose the raw material to create it through its entire life cycle, building, blending it, maintaining it, changing a part in it, and then disassembling and recycling it. Because to recycle, you need to know that a given part was changed, and it's no longer iron, but it's another metal now. Okay? And so to support these multiple sources, they believe that knowledge graph is the perfect structure. In other words, they state that to enable circular economy, you need a data economy on top of the knowledge graph. Now, most of you in these rooms are very young, too young to have used one of these books. Still have a copy in my that, which tell you how old I'm. So these were the books you would buy, the yellow pages. You go on the web to find a book. Of course, you no longer use that because we have a new verb in English or in Globish, which is to Google. This verb is used every day, and that's how you find information. And that's how humans do it now on the web. Now, how do we do it for data? So one of the work we've done the past year in my team was to try to improve access to data sets. So there are many tasks in accessing data sets. I will focus on two of them, crawling and indexing. So the first work we've done in a collaboration with the Quant search engine was to train machine learning system to predict if a given URI is going to be referenced and provide data. Why would you like to do that? Because when you crawl, one of the most costly actions is a network attack. So you want to do it when you have a good chance to get a result. And for some URIs, there are some hints that it's hopeless. You will not get something. You will not get audio. Or on the other side, in some URIs, there are hints that, yes, it's likely to give you some turtle. And that's what we did in that work with Huang. We train a system to take URIs and to predict the likelihood that this URI is going to provide data. And we get a high enough confidence to rank in the stack of all the URIs you have to crawl, to rank first the one which are the most likely to give you data so that you get the data sooner. On the other side, we recently released an open source software called Index. So good luck pronouncing that. This Index is a GitHub approach to maintaining an index of the knowledge graph and of the rules to index them. So when you connect to the index of GitHub, you will see a number of data sets identified, seeds to discover data sets, but also a number of rules that are going to be run on this data set in order to generate descriptions of this data set, maintain description of this data set. So it's a declarative framework of extraction rules to manage a GitHub index, an RDF index of RDF sources. That's the back end. There is you can build then on top of it a number of things. So for instance, you can use this index to do distributed query solving if you want. One of the front end we provided is called cartography, and it's a visualization of the content of the index. So this allows us to know that, for instance, a given data set is linked to another one through a shared vocabulary. Or in other words, which are the data sets that use that vocabulary. That's what you are visualizing here, the links between the vocabularies and the environments. Another example of analysis, we use two different methods to try to geolocate the data set. And then we start to analyze what we see. For instance, we wonder where we got it wrong or what is happening for having an empty diagonal in our index. Is it the truth? Or are we missing something? Do we have the bad seeds? Is something happening in the community that explain that? This is still something for us to expand. And of course, the interest also of having such a front end is to encourage people to describe their data set. So if you do not appear in the index, you have a data set, first reaction will be disappointment. And we count on that so that you will go to that last tool, which is called metadata-matic, which is a semi-automated way of describing your data set. You put the endpoint of your data set. It pre-fills what you can fill in the description, and then you can fill the rest. It helps you create the description so that it will become visible. Description use very well-known vocabulary, such as decat, boy, and so on, because we didn't reinvent them. On top of this index, you can start to do smarter things or more customized things. So yesterday, Natalie told us about the number of fairness methods that were available, right? And so one thing you can do on index, for instance, is take one of these and write the rule and push it to GitHub so that now it is calculated on all the data sets of the index. So she mentioned one of Alban Gandon, which is a fair checker. Okay, and so that's what we did. We reproduced the algorithm of Alban using the declarative language we have in index. We pushed it to the GitHub, and now for all the data sets, we calculate the result of the fair checker on that data set. And you can do that for any metrics. So for instance, we took a completely different metric from Anderson, which is the metrics which is trying to capture the accountability for a data set. How much you know about people who are accountable for things in that data. And this is a very, very structured way of calculating a metric because it's based on a series of questions, of weighted questions and answers. But we can do exactly the same for that metric and push it to the index and then calculate it on all the data sets. And as a result, you can calculate them and compare them. So the nice thing is that not only you have the declarative version of these metrics, you can compare the formula, but you can also compare the results on the entire index. And you can see where they agree or where here they disagree. They are not capturing the same thing about the data set. And this helps you choose a metric over another, for instance, or decide that you need your own metrics and push it to index to calculate. Okay. So the first family of scenario was about identifying the data sets, avoiding the silo, linking them together, building catalogs of data sets, and contributing to the urbanisms of the information system, as we saw even in the testimony from industry. The second category of scenario I wanted to focus on today are all the scenarios where we use knowledge graph to contextualize either data, so data inside the company, or queries or requests or recommendations. So let's go to industry again. eBay has a knowledge graph. Okay. They use it to have extra user item connectivity. So in other words, what they want is to capture and contextualize the items of their catalogs. Why do they want to do that? If they just look at what you do on eBay, they will see that Philip is interested in forks, good. Then Philips is interested in knives, good. And that's it. With the knowledge graph, what they know is that forks and knives are kitchen business lines. And so therefore, Philips has something with the kitchen these days. That's what it means to contextualize. Okay? And so that helps them build better recommendation because they might search in the kitchen area if they push something else to fill it. And also it helps them explain a recommendation. If they come to a new recommendation saying, oh, you should look at the spoons, they can also explain to Philip, well, we thought about spoon because you look at the knife, you look at the forks, they're all in the kitchen, spoons are in the kitchen. Maybe you're interested in spoons, okay? Okay, no surprise, Amazon does the same. They have what they call a common sense knowledge graph to aid product recommendation. And guess what? It captures relationship between the products and the human context, the role, the function, the audience, exactly the same, in fact. What's interesting in their testimony, in addition to what we saw before, is that they have activities on using LLMs to extract the common sense relationship. Because now they want to build this knowledge graph. And this knowledge graph contains a very special kind of knowledge, which is common sense, which is not necessarily the one we find in most of the data sets right now. Okay? And in fact, I already mentioned that before when I talked about the robots. In my team, we work on a robot worked by Cabrillo et al. And we use NLP technique to, and a special corpora, so for instance, books for children, to extract common sense knowledge and provide it to the robot. So the idea is that if you want to have a robot like that help elderly people stay at home, and you want now the robots to go and fetch the spoon, if you are a human, if you ask Nicola to fetch the spoon, what Nicola is going to do is he's not going to look for the spoon here. It's first going to go to the kitchen and then looks for the spoon because he knows that the spoon is in the kitchen. He has this common sense knowledge. And so that's what we train the system to learn from text, to extract the common places where we find some objects and build a knowledge graph, an RDF knowledge graph, to represent and then use it so that the robot moves to the kitchen before turning on the image recognition algorithm. An interesting thing also is that because you do that in RDF, because it's an open format, as soon as one of the robots learn that, all the robots know it because they all share the RDF. Many of the examples I gave you from now, until now are from France, Europe, or US. I didn't want to bias my talk. So here is the knowledge graph of Alibaba. It's called AliCoco. I love the name. AliCoco is a large-scale e-commerce. Alibaba is a large-scale e-commerce site, and AliCoco is a large-scale e-commerce cognitive concept net, aka knowledge graph. It's used as unified data foundation for user knowledge, product, and content understanding. Same thing, same story on the other side of the earth. Helping search and recommendation, better recognize the context. Here goes the context word, it's here. And again, they have worked on semi-automatically constructing this knowledge graph. So again, they use it for contextualization. And again, they have invested in methods for semi-automatically constructing. So one of the PhD, which is well advanced in my team now, is looking at this problem of constructing the knowledge. So you remember we are hosting the Wikipedia French chapter. And so we looked at what we could do to have alternative method to extract some object. And we look at it as a task where you provide a Wikipedia article, or at least part of it, for instance, the abstract. You provide a shackle shape which captures the pattern of the graph you want to extract. So the shape gives you the target. I want to extract this type of graphs. Okay? And then you train a model to extract graphs that correspond to that shape. That's the task we are interested in. I want to focus, to target, to extract people with their name, first name, and birthday. That's what I want, for instance. And so I put it in my shape and I train myself. And so what Célian Ringwald did was to study that pipeline and also to study the impact of the linearization of the graph on the results. Because when you have a language model, you have to choose a linearization for the graph. You have no choice. So we extracted a dual base from DBpedia containing abstracts and knowledge graph that we validated up front. Then we looked at the different ways of linearizing data and graphs in the literature. So in the literature, it's essentially list and tags. We included all the syntaxes of W3C, so XML, JSON, and triple total, and we added one custom in-house syntax, which we call the light turtle, which is even closer to English. And in fact, what we did is we removed from the language a thing that we don't need to predict. I don't need the model to predict the prefix and the namespace. I know that they are available in prefixes. So I don't need that. I want to really focus on the piece of RDF to be extracted. And so we have a light turtle syntax that does that. The other things we wanted to do is to do that with small language model. I didn't want to do it with LLM. I wanted to do it with small, be able to run it on small machine rapidly, efficiently, okay? So we use BART and T5, and we changed nothing. We use them off the shelf, like this. We introduced a number of metrics that I will not detail here to validate the triple produced, the classical metric on the task, also the resource consumption metric, and we also provide metrics for characterizing the behavior. Is it stable? Is our model stable? For instance, how fast does it find the extraction and how stable it is? And so we ran all of them, all the configuration we had. And the interesting thing is that at the top of this, we find this model here, which is using light turtle, which has very good performances if you look here. It has very, very low resource consumption. Between 8 and 10 minutes to train, very fast and very efficient. That's the thing we like about this result. All right, third family of applications. I call them linking all forms of intelligence because I believe, so at WCC, there is this motto saying WCC is here to lead the web to its full potential, whatever the full potential is, which I like. And I believe that in that potential, the web, there is the one of linking all forms of intelligence. I think the web has this potential. It is up to us to achieve it. And in that vision of the web, I think knowledge graph has a key role to play. And I think I'm not the only one. During the summer, Samsung bought a company called Oxford Semantic Technology. Many of you know it. It's Ianorak, known in the community. They produce a very nice software called RDFox. And so we knew it was coming because Samsung was investing in them since 2018, I guess. And now they bought it. What I like in the statement, or what I noticed in the statement of Samsung is that, so again, enhance the understanding of product or services and service usage, integrate connected data. So far, we find all what we've seen in other testimony. Enable rapid information retrieval and recommendation. Again, we found it in other testimony, but one of the sentences I noticed in their press release was, first of all, they intend to run that stack on any device. That means running on the phones, on the tablets, on the TV, on the computers of Samsung. You will have that stack available. And why do they want that? It's because they believe it's a key technology for realizing more sophisticated AI. In other words, they will ensure it's available in all their devices because they're going to build their AI stack on top of it. So this is at the edge of the network. Inside the network, if you look at what Nokia is doing, for instance, they also use knowledge graph. In their case, they use it to represent the network itself and the network component, the routers, the antennas, the thing like that, and to reason on it in order to do energy management. And what they say in their press release is that they believe they are going to save billions of dollars in terms of energy by doing that, by having a knowledge graph that allows them to intelligently manage the network. Big company also, Bosch, they went so far as to actually develop and release their own stack of products for managing knowledge graph. So they have an entire stack, which is called the Bosch semantic stack, to connect and access all their backend system and to leverage data across the entire product lifecycle. They insist on using open standards also, which is really nice. And they, among the interests they see in using the knowledge graph and the reason why they invest in that is this sentence: they believe in knowledge-infused machine learning, which is combining explicit and contextualized domain knowledge, aka symbolic AI, with data-driven machine learning method, aka sub-symbolic AI. They believe that they are going to use that not only to drive their AI process, so the entire AI workflow would rely on a knowledge graph, but also to enable neuro-symbolic AI approach. So this is one of the hottest topic in my team too, of course. There's no surprise. Many teams are working on that right now. We started to look at this convergence almost now 10 years ago in the case of prediction for hospitalization. So one of the first attempts we did was to take this kind of data, which are data from the general practitioner in France. So the doctor you're going to see when you have a cold or something bad. And from these data, what we try to do is to predict whether there will be an hospitalization within the next 6 months for you. So you can train a system to do it directly from the data. What we tested is what happens when, before you do that, you include knowledge from knowledge graph in the medical domain. So you infuse your data with knowledge about the drugs, about the disease, about the medical acts that are going to do, and then you train the model to predict. And what we show is that in some cases, we can boost the prediction. We also showed again that everything depends on the quality of your data, because in the end, we can see semantics as an amplifier, which means if your data is good quality, you amplify the quality. If you have noise, you amplify the noise. And you learn on amplified noise. So there is a drawback in this injection. So from that first stage, we decided to look at what we could do in other domains. The second scenario we looked at is the cultural domain. We used the data set called Joconde database, which is actually hosted in Paris. It's the data set of many museums, including Le Louvre. And the nice thing about this data set is that it contains 350,000 images of artworks, so painting, sculpture, drawings, all sorts of arts, and the RDF version of the metadata of the catalog, what the curators of the museum said about these images. So we have those, which is nice, because what we can do is exactly what Bosch called knowledge-infused AI, which is we use RDF, for instance, to generate training sets for classifier. So I can say, okay, generate for me a very good data set to train on horses. Okay, then I train a classifier to recognize horses automatically. And I use that classifier on my entire images to predict whether there is a horse, and the result is itself in RDF and goes in the base. So now in the base, I have what the curator has said, what was inferred from the schemata of the known state, and what was classified by my classifier. And I can compare them. So I can compete on the one hand between reasoning and learning. And what is interesting, then when I contrast them, I can detect problems in the quality of my data. I can detect noises and silences. I can detect that here the curator says there was a horse, but my classifier says, sorry, I didn't see the horse. And here, the curator never said there was a horse, and we say, there is a big horse in this one. Okay. So we can improve quality. If you look at Walmart, they're doing all of the above, everything we mentioned so far. So representing the products, the context, leveraging the semantics of the schemata, searching and recommending. And also they mentioned something that more and more people do, which is answering questions directly on the knowledge graph. Answering question, meaning answering question in natural language. Many people are now building or looking at chatbots on top of the knowledge. It's a very topic that comes with some of the latest techniques such as RAG. Okay. So LLMs everywhere, good and bad, a bit like the sugar, right? You're getting them everywhere. And so we also look at them in my team, but we have this position that right now we feel confident to use them on two tasks. Two tasks which are essentially linked to human interaction. The first task is the one I mentioned before, extraction of knowledge from natural language text. And the second task is natural language query on linked data. That's the two tasks on which we focus, because other tasks we are still not very confident. And so we apply it to chemistry. So I was really amazed when one of my chemist colleagues at Tunis came to my office and told me that in his department in chemistry, he has a mass spectrometer system to analyze samples of tissues. And the output, that mass spectrometer, he had coded it to produce RDA. Which is amazing for me, because it means that they are in a position where they already have huge amounts of knowledge available in knowledge graph in the domain, from these sources, but also from catalogs. And their analyzers now are also producing RDF, which means we are in a position where we can use the power for integrating data of RDF to have one graph that links everything. And so that's what they did. But their main problem then is that not every case took Sparkle as a foreign language. They don't speak Sparkle. So what we decided is to train on that system to have a chatbot that helps the chemist formulate the right query. With one constraint from the beginning, we want the approach to explain every step it does so that the chemist can decide whether he trusts or not the result. So we do RAG++. We augment the context with a number of techniques to sample the graph, the schema, and contextualize the request as much as possible, but also to inject knowledge that the model has never seen before. The knowledge, by definition, the model could never have seen the knowledge graph going out of the spectrometer. So we inject that. We use these and the schema to augment the context, and then we, on the context review, we move to the task of formulating a Sparkle query on the integrated knowledge graph. And we answer. So it looks like this. This is a question from a chemist. Please don't ask me to explain the question. He told me it was in English. I didn't believe him. I have no idea what he's asking. Apparently, makes sense. And if we do that, with that cost on an LLM, we are able to generate these answers, and we are also able to document each step. So I cannot scroll down here, but below are each and every step, what entity we recognize, what Sparkle query we proposed, how it performed, and so on. So we explain each and every step of the solving so that the chemist can decide whether or not it was what he was asking and he's getting. We also explain when we fail. Okay, here we fail. we explain why we failed, and we show where we failed, so that if the chemist knows how to repair what went wrong, it can do it also. And so we are now starting a big project for the next 4 years to do that at every omics level, integrating omics. So we're starting a project between France and Switzerland on that topic. With one future approach, modification we would like to do is to integrate in the interaction with the user more than text, because these LLMs, they are good at chatting. Okay, but a chemist, when he asks for a molecule, he'd rather see it. He needs a visualization of the molecule, not a text talking about the molecule. So what we are now working on is integrating in the LLM approach and so I don't like the word, but the agent-based, like line chain and graph and prompting. I don't like the use of agent here. We can discuss that after if you want. We are integrating there the ability not only to select tools when accessing the data, such as what we do in RAG, but also select tools when producing the answer for the visualization. We have a library in the team, which is called LLMs, which is dedicated to visualize knowledge graph. I mean, you can generate a visualization like this one from an RDF graph. Again, it's open source. It's used for visual mining of RDF graph. It's used for incremental data exploration, where you start from a query, and then on the result of the query, you generate sub-queries to focus on some sub-aspects. It's used for data quality exploration to detect problems in the data. It's also able to adapt to certain types of data, such as temporal data visualization. So here we are visualizing data from DBpedia about the rock band Queen and Freddie Mercury, and visualizing it and for instance, detecting when Freddie went solo and what was the impact on the group. And we also have visualization for more complex results, such as the result of association rule mining on the data. This is visualizing the result of the mining on an RDF, which results in a set of suggested association rules found in the data. And the idea is now to use the chatbot we have to generate interfaces that integrates this kind of result in the answer. Okay, let me conclude. So I really believe, and I don't need to convince you, that there is a growing potential now in knowledge graph in general. So I started my PhD in 1999, so the year after it started, but there were many communities already active on knowledge representation at the time. There was the description logic workshop, which was really strong. ECAO was already existing. And if you were going to any of these conferences, ICCS, at one point someone would quote Francis Bacon and say, knowledge is power, and everyone would say, yes. This is a quote you hear all the time, knowledge is power. But when is the last time you experienced the power of knowledge? Beyond that quote. So I want you to do the experiment with me. I'm going to show you a slide. I just want you to read it. That's the only thing I have. Okay. Because I have knowledge on how your visual cortex works, I have power over you. I can predict and manipulate you over 5 seconds. Okay? This is what it means when we say knowledge is powerful. When we have knowledge about you, we can manipulate you. You lose freedom. That's what it says. So we have a responsibility to target useful and beneficial knowledge. When we choose which data set knowledge, we need to be contributing to useful and beneficial knowledge. We need to be sure that we are not designing bad AI, bad systems. We want benevolent and beneficial AI by design, not the opposite. So it's one of the reasons why the latest paper I wrote is not a computer science paper. It's a paper at AAAI IAIS that I just published, which is called Pay Attention, where I defended with my colleague Frank the fact that I believe one of the biggest problems now on the web is the use of the knowledge we have about the user plus AI techniques to capture your attention and manipulate on a large scale. And I believe this calls for regulation. I believe this market of attention, this approach of algorithmic emotional governance should be regulated. We need to do something about that. We are going in the very, very bad direction if we don't. The second quote I wanted to put here is a quote from Lessig, which I like. And he wrote a book about the fact that when we write a code, we are writing a code. And it's true if you consider a platform like Facebook, 3 billion users, you change the code of Facebook, you're impacting how Facebook works for this 3 billion, you are changing the laws happening on Facebook. And this is a very big problem, because when you look at things such as the terms and conditions of the different services we are using, if you want to make sure what PayPal is asking from you, you need to read terms and conditions that are longer than Hamlet before accept. And no one does that. Okay. Then iTunes is somewhere between Macbeth and Hamlet. So it's not realistic to ask you to check the box and say, I agree on this. This is true for terms and conditions, but I also believe that we are having a growing equivalent with ontology commitment. Peter reminded us yesterday in the presentation that when we decide to use an ontology, such as the one of Wikidata, and we decide to use the class of the classes of them, we are committing to that definition. We must be careful which one. He identifies 3 of them. Which one should I use? Which commitment should I make? And this is complex. The more we reuse ontology, the more the ontology are complex, the more this commitment requires work on explaining what the commitment is, having a human interaction that explain the human what they are committing to, and so on. Okay? When you align with other commitments, well, with ontology, there are 50 shades of that. You can extend an ontology, you can do a same as, you can do a related to in scopes. This coupling is becoming more and more complex, and it still is an open question. And when you put these codes together, you can create a new code for fun, saying that knowledge encoding is a power law, in the sense that we have many knowledge out there, which has already benefited from knowledge extraction techniques, which are Wikipedia, but in fact, we are not covering the long tail. All these small patterns, small data sets, small topics are not covered. We're not extracting them, and it's costing a fortune. So how are we going to perform sustainable, frugal, and affordable knowledge augmentation in the years to come? And when I say augmentation, it's not only for machine, but it's also for us. How are we going to reconcile user-centric and reusable knowledge engineering? How are we going to avoid all the problem of quality or spam in knowledge graph? We find spam in your data set now. Okay. So in my talk, I defended the position that knowledge without intelligence is a highly perishable resource, that intelligence without knowledge is due to stagnation, and so we need to work on them jointly. And beyond that, we also have the opportunity right now, especially on the web, to reconcile 2 terms, AI and IA. AI for artificial intelligence, and IA, which was quoted in the same years for intelligence amplification, intelligence augmentation. In other words, keeping the human in mind, keeping the human in the loop, keeping the human the center of our question. Because on the web, we now have, with knowledge graph and the standard, we have the ability to identify everything, which is great. We have the ability to describe and link this description, decentralize them, which is great. We have the ability to access them and compute and distribute the computation. Awesome. we have all the schema to represent absolutely everything, the topics we are talking about, the computation we are performing. You even have ontologies to describe neural network now. But in the end, the full potential is to link absolutely all kinds of intelligence, artificial and that's what we can achieve, and that's what I would like to see before I leave. And with that, I thank you for your attention.